Here we go with the periodic table guided notes. We're going to go through slides 1 through 24. Here, we're not going to do the end of them in this screencast. I will do that in the next one. So, the periodic table. We're looking at a periodic table. This is the most beautiful periodic table that has possibly ever existed. This is something I would like to put in my house. But the original periodic table was developed by various scientists. John Newlands was an English chemist who discovered when he arranged the properties in order of increasing atomic mass, he would there would be a pattern, much like musical scales. So he called it the law of octaves. Now he was not able to publish his periodic table in a way that people could understand it. So he didn't get a lot of credit for it, but he still was one of the individuals. There were many scientists at the time that were doing research like this to try to arrange and find meaning to the different patterns of the elements. But Dmitri Mendeleev is the one who really nailed it. In 1969, when he was writing a textbook, he arranged all 63 known elements, and he did this in a way that was similar. He did arrange them in order of increasing atomic mass to some extent. However, he used properties of the elements to arrange them more so than the atomic mass, because he saw discrepancies in the atomic mass pattern. He also left gaps in his periodic table, and that's the key where Mendeleev's periodic table is superior to any of the other periodic tables of the time. He left gaps because he knew there were elements that were not yet discovered. And so his periodic table allowed you to make predictions about the elements, and because it was based on their properties. And that's the key to Mendeleev's periodic table. So this is the example of what Mendeleev's periodic table looked like, one of his first periodic tables. And you can see there's similarities to our periodic table, the modern periodic table. So you have a group of elements that form one bond with or two bonds with oxygen, like hydrogen forms water, H2O. Lithium also does that, and sodium and potassium. And so he put them into a first column, and then he has a second column there where they form one bond to oxygen. And so you have beryllium, or a 1-to-1 ratio with oxygen, and you have beryllium, magnesium, and calcium in that column, just the same as we have that in our column 2 on the periodic table. And then he had column 3 where they form a +3 charge, or they form this ratio when they bond to oxygen. And then you had boron, aluminum, and then he had elements there that were not yet discovered. He had Eka aluminum, right? That's this guy right here, and he's a key element in the success of Mendeleev's periodic table. And so he had Eka aluminum, Eka boron, and Eka silicon. They were elements that he had predicted that would exist that were not yet discovered. And so Eka aluminum is gallium, Eka boron is scandium, and then Eka silicon is germanium. And you can see that his predictions are very close to the reality of the properties of those elements. That's the key to Mendeleev's periodic table, is that it was used to predict the properties. And so maybe we actually made the periodic table by playing Tetris. I mean, it kind of looks like that, right? So this video is very good. You should watch this video. It talks about, Mendeleev's discovery of the periodic table. You'll see some similarities in the way that this gentleman describes Mendeleev's life and the way that Hank Green described his life. But the modern periodic table was developed over time. What happened was they took Mendeleev's periodic table as the starting point, and then they've added to that and refined it, as we do in science. We refine the ideas based on new data. And so Henry Moseley studied X-ray spectra. What he did was he shined X-rays at the crystals of the different elements, and he noticed that there was a pattern. The pattern was they changed as the atomic mass increased. However, he realized that it wasn't exactly atomic mass because some of the elements on the periodic table are a little out of whack when it comes to atomic mass. And so he realized that it was atomic number and not atomic mass. You see, Mendeleev didn't know about protons, neutrons, and electrons. They just didn't know about those at that point in time. But when Moseley discovered this, he actually then discovered the proton and atomic number. And so atomic number, when you arrange the elements by increasing atomic number, then all the discrepancies that came from increasing atomic mass disappeared. Okay, and the periodic table becomes then perfect. So the periodic law is the principle of chemical periodicity. It is when elements are arranged according to their atomic numbers, elements with similar properties appear at regular intervals. This is very important because periodic law allows you to predict the patterns of the elements based upon their family or the column that they're in, or you can predict elements based on the series, based upon the row that they're in. And so it all comes down to valence electrons. Valence electrons are the reason why elements do the things that they do. We love chemistry cat memes, right? We just love them. And so the valence electrons are the outermost electrons. They're the ones on the outside of the element, and they're the ones that are involved in chemical reactions because they're on the outside. And the particles that are on the outside can interact with particles on the outside of other elements, and what happens is you have chemical reactions that happen when valence electrons are transferred, when valence electrons are shared, and this results in ionic compounds being formed or covalent compounds being formed, and it's really the heart of chemistry is valence electrons. And so it's very important for you to be able to predict how many valence electrons an atom has. And so if you look at the periodic table, it helps us with this. So the first column on your periodic table is where you have one valence electron. In your second column of the periodic table, you have two valence electrons. And you'll notice that helium is over here because helium is a noble gas. It doesn't react with very much, with anything, actually. So that's why it's placed over here. But it could be placed here, right, above beryllium, but it's not. It's placed over here because it's a noble gas. And then you have three valence electrons over here with boron and aluminum. And then you have four valence electrons with carbon and silicon, five valence electrons with nitrogen, right, and phosphorus, and then six valence electrons with oxygen and sulfur, seven valence electrons with the halogens with fluorine and chlorine and bromine and iodine, right? And then you have eight valence electrons in the last column, the noble gases. Remember, helium, noble gas, but it has two valence electrons. And so the organization of the periodic table is with groups, the families, they are the columns on your periodic table, and then a period of elements is a row or a series, right? They're in the same period. The reason why elements in the same group have the same properties or similar properties, especially with reactivity, they react in a very similar way because they have the same number of valence electrons. Elements in a period will react in a similar way because they have the same number of electron shells. So they have the same number of rows of electrons, of layers of electrons. Okay, and that's what makes a period similar to each other. And so if you want to group the elements into different categories, one of the categories you can use is their metallic nature. And so you have metals on the left-hand side of your periodic table, you have nonmetals on the right-hand side of your periodic table, except for hydrogen. Hydrogen is a nonmetal that's over there on the left-hand side because he only has one valence electron. But all the rest of the nonmetals are over here on the right-hand side. And then you have metals that are on the what we call the left-hand side, but you notice that it's most of the periodic table. Most of the periodic table is made up of metals. And then you have the middle of the periodic table, and what we call the middle of the periodic table are the metalloids. The metalloids are the ones in between the metals and the nonmetals. They kind of have properties of metals and they have properties of nonmetals because of the way that they, because of their electron arrangement and the number of protons in their nucleus and all kinds of good stuff that we're going to study. So metals, they have these various properties, okay, that you can say all metals or most metals have. Most metals are good conductors of heat and electricity. They are malleable, meaning that they can be hammered. So you can hammer metals, and that makes them malleable. Ductile, meaning that they're made into wires, that you can draw them out into wires. And you notice that copper is one of these, right? And we use copper for wires a lot. They reflect light, meaning that they're shiny. They have high densities, meaning that they tend to sink in water, right? They have high melting points, meaning that they're solids at room temperature. And they easily lose electrons. That's the part that makes them metals, is that they easily lose electrons because they have low electronegativity values, because they have a low effective nuclear charge. And we'll talk about those things later. And they also corrode because they react because they lose electrons. Right? Then we have nonmetals. Nonmetals are the opposite of metals. So all those properties that we had for metals, nonmetals have the opposite of those properties. So they're not good conductors of heat and electricity. They are dull, meaning that they're not shiny. They're brittle, meaning that you can't hammer them, or they shatter. They have low melting points, meaning that they're gases, right? So the noble gases are all nonmetals, and they have a low melting point because they're gases, right? Low densities, meaning that they tend to float in water, or that they're gases because those are definitely less dense than water, right? They're solids and liquids and gases at room temperature. There's all kinds of examples of those. And they tend to gain electrons when they form compounds. And so that's a key part of their reactivity, is that they gain electrons when they form compounds. And so metalloids are in between. The metalloids are commonly boron, silicon, germanium, arsenic, and antimony. And then you have tellurium. You could put tellurium in there if you want to. And then astatine you could throw in there if you wanted to. It's kind of silly because astatine is like the rarest element on the periodic table. It just really doesn't readily occur in nature, but that's fine. They are solids at room temperature. All of them are solids at room temperature, but they're shiny or dull. So if you notice them, and I would love to be able to show you my sample of silicon, but it's in my classroom, and we're not in my classroom right now. They are malleable, meaning that they can be hammered sometimes. Some of them are not malleable, like silicon's not malleable. You can't hammer silicon. But they are ductile. Sometimes they can be drawn into wires. They are called semiconductors. Okay, they are called semiconductors because they don't conduct in their element form, but they do conduct when you bond them to something. And so that's what makes them semiconductors. So silicon we use for computer chips because silicon isn't conductive, right? But then when you bond it to stuff, then it becomes conductive, so you can make a transistor out of it. And so then we have these various groups on the periodic table that we're going to look into in more detail. Group 1, the alkali metals, they have one valence electron. They're in here, column 1 on your periodic table. They are very reactive. They're not found in nature by themselves. They're very soft metals. They have one valence electron. And I believe you saw me put a bunch of alkali metals in water for one of the Fire Friday demonstrations that we did online. Then you have group 2, which is the alkaline earth metals. They form bases with water as well, and they're very reactive, but not nearly as reactive as the first column. They are also not really found in nature by themselves because of that, because they're very reactive. And so here's some examples of them down at the bottom here. Beryllium and calcium and strontium and radium. Radium actually used to be used for glow-in-the-dark watches, but then they realized the reason why they glow in the dark is because it's radioactive, and that gives you cancer, and that's a bad thing. Okay, then we're also going to look on the right-hand side of our periodic table. We have the halogens and the noble gases. Halogens are right here, column 17. That means salt former because they form salts with metals, right? They're the most reactive of the nonmetals, and they have 7 valence electrons. When you go to the last column on the right, you have the noble gases. They are very unreactive. They're all gases at room temperature, and they have a full set of valence electrons. That's what makes them unreactive, is that they have a full set of valence electrons. So then you also have the transition metals. They are in the middle of your periodic table. Okay, they are the metals that we think of when we think of metals, right? Iron's in here, cobalt, nickel, like the metals that we think of as metals. They're in the transition metals. They have a lot of different properties, but they're very metally, right? They generally use their outermost 2 electrons when they react with stuff, but they can use more than 2 when they react with stuff as well. So that makes them very different. And so that's the end of this one. This is the next slide that we're going to. So you can stop right here. You should be able to fill out everything from your guided notes through this.